Hallo, guten Morgen und herzlich willkommen bei der INDUSTRY.forwardEXPO, unserem Industriefestival für den deutschsprachigen Raum. Bei mir heute zu Gast auf der Electronic Stage ist Christoph Bianchi, Director Business Strategy bei Ansys. Hi Christoph, pleasure having you here.
Hi, Christian.
Christoph wird sprechen über Simulation. Und zwar Simulation als das Herzstück und ein Muss in der nachhaltigen Produktentwicklung. Christoph wird das auf Englisch tun. An dieser Stelle möchte ich mich kurz halten und zu Christoph kommen und habe da nur noch zu sagen, Christoph, the stage is yours.
Thank you, Christian. Well, guten Morgen, and thank you for dialing in this early of the day. So I hope everyone had a good cup of coffee or tea, and so that I can start the presentation. Let me just share my screen here. Good. So what I would like to discuss with you today or this morning is how simulation can be deployed and used purposefully to develop more sustainable products. After a general overview, I will share with you a few examples that were picked randomly across diverse applications and domains. And I will encourage you to ask a first question, insight, and comments in the second part of the keynote. Typical sustainability decisions made early during product design have material consequences for a business that impact time to market, quality and cost, with recalls and non-compliance penalties that can cost billions of dollars to your brand. The ultimate challenge remains that these early decisions are made with no visibility and must consider product design, production, and use, including the product itself, its packaging and logistics, as well as the way it is discarded at the end of its life. And the complexity of the decisions stretch across international governance bodies and global concern for carbon footprint, water consumption, and energy usage. So how can we address this process? A study performed by the European Commission estimates that over 80% of all product-related environmental impact are determined during the design phase of a product. Whether it's about the selection of materials, as well as the manufacturing process and optimization, or the design trade-offs, this is a multi-dimensional optimization where more than often the data set upon which decisions are made or choices are made is incomplete. And this is where simulation is an essential contributor to solving these complex engineering challenges. What do I mean by simulation? What is it really? Well, we can say that simulation is a process of modeling the effects of the laws of nature onto your future product without having to create a physical prototype. In other words, simulation reduces the need of prototypes. In the late 1800s, beginning of the 20th century, famous mathematicians and physicists created mathematical models for most of the laws of nature. From Isaac Newton on the top here, who discovered the laws of gravitation, to Edouard Branly, who modeled radioconduction and telemechanics. From Satyendranath Bose, who worked with Louis de Broglie, Marie Curie, and Albert Einstein, to Ludwig Boltzmann, who created models for the kinetic theory of gases. All these scientists had one thing in common: understand the laws of nature and model it with mathematical tools. Now, here, as you can see, we took some examples, the ones from Navier-Stokes, who invented the fluid dynamic modeling on the top left, Maxwell, who spent a lifetime with electromagnetism, that served as a basis for Nikola Tesla's work on alternative current, Laplace and its use of transform to solve mechanics, Ernst Mach in acoustics. You all notice that Ernst Mach equations are not on this slide, right? Or Joseph Fourier, who modeled the heat propagation by transforming an equation into a trigonometric converging series, and so on and so forth. All these inventors transpose the laws of nature into differential equations. And what we've been doing at Ansys for the past 50 years is simply to model these equations into computer software, including their boundary conditions, to provide solutions and results after refining and optimizing this calculation, so that you can predict extremely accurately the behavior of any object or product under any set of conditions, even if you don't know all of these conditions. So in other words, we can say that simulation is a process of modeling the laws of nature for your future product without having to create a prototype. once again, in other words, simulation reduces the need for physical prototyping. Now, over the past 50 years, engineers like all of us on the phone have developed solutions and design methods relying on simulation to perfect the art of creating faster, cheaper, and better products. Our customers, the engineering community at large, has become extremely effective and mastered these methods in order to find the best solutions and trade-offs in this tridimensional space. But sustainability and the impact on resources and the environment were seldom a high priority. And when we add sustainability dimension and the growing concern and care about the protection of the ecosystem we live in, this completely breaks the pattern. There are way more parameters to take into consideration, and the engineering methods, processes that we built and perfected over time now limit our potential. We have to reset and restart by considering this fourth dimension with the same or even higher level of priority over cost, performance, and quality. And this creates a much more complex problem to solve. And of course, as engineers, we love complex problems to solve. And we're lucky to have simulation boosted by artificial intelligence and machine learning to reinvent our innovation methods in order to recreate better, earth-friendly products. Engineering simulation fosters radically new ways of design thinking that include the thorough analysis of where energy is consumed and how it's being used, the assessment of root causes of waste to develop alternative processes and stop creating waste in the first place. It also helps with a real-time examination during the full product life cycle of the resource utilization using digital twins. Now, whether we focus on greenhouse gas emission, energy, materials, or environmental and human impact, simulation solutions save raw materials and ultimately reduce carbon footprint by replacing physical testing with digital testing and accelerating time to market. But perhaps more significantly, when used as part of the design and development phase, simulation can help build effective and efficient products that are integral to meeting the environmental sustainability needs of the future. And applying engineering simulation solution reduces costs, shortens times to market, and reduces risk of failure by improving product quality. Now, out of these four main categories, simulation has been and continue to be applied to multiple domains and industries, such as oil and gas, automotive, high-tech, industrial, construction, consumer, agronomy, and healthcare. And in the next few slides, I'll focus on a random selection of applications and dive deeper into the usage of simulation and its benefits. In industrial plants, flare stacks are primarily used for burning of flammable gas released by safety valves during unplanned or planned overpressuring of plant equipment. And during planned and partial plant startup and shutdowns, they're also often used for the plant combustion of gases over a relatively short period of time. The burning of gas releases CO, carbon monoxide, and NOx, nitric oxide, and nitrogen dioxide, which are harmful to the environment. The reducing emission and controlling dispersion of the flare stack is a necessity in order to meet regulatory emission limits, as well as minimize the damaging effect of the heat radiating from the flare onto the surrounding buildings, workers, and equipment, as you see in the little orange graph on a gray background here, heat wave on the structure. Not only simulation can predict with high accuracy 3D models the flaring and dispersion of equipment, but with the ability to change and simulate the fuel composition, it gives a fast emission prediction based on reactor network modeling. And with real-time models, coupled with sensors and connected industrial systems, it can be built into digital twins, allowing for predictive maintenance and dynamic control of the flare system, resulting in safer operation and minimizing emission of harmful pollutants. This is a completely different project. Here we demonstrate the use of engineering simulation for smart urbanization. Computational fluid dynamics simulation was used to improve the renovation of Brussels state administrative federal government buildings. It's a site of more than 14,000 square meters of office space that is to be turned into housing, apartment building, offices, shops, parks, and schools. Here, what we simulate is the effect of wind. And the wind analysis is useful in studying many parameters related to a site's user comfort, in this case, including high-rise buildings and green spaces. In some instances, the building will act as a shield, a screen, and improve the comfort, but in others, the wind pattern could cause significant discomfort and might even be dangerous to both the pedestrians and the occupants. Several different phenomena can occur, such as channeling and wedge effects that lead to local wind acceleration and increased turbulence. These phenomena can contribute to the discomfort for the people located at the ground level, terraces, and balconies. And the wind effect can also damage vegetation, but also generate an unwanted pressure effect on the building that create whistling effect or material damage. There is a standard in construction in Europe, and this is measuring the discomfort metric, and that corresponds to a wind speed at about 1.70 meter above ground, the average human height, that should not exceed 5 meters per second more than 220 hours per year. And here, simulation provides a quantifiable assessment of a project performance, of course, prior to building any prototype. Another cool example of the use of simulation for sustainability is the design of recycling plants. First in Europe, and now in the US, recycle centers are coming to depend on short wavelength infrared sensors, SWIRs, spectroscopy that helps sort out plastic in the waste stream. The complete equipment is usually between 512 or 1024 low-cost SWIR elements in a line scan. And these cameras, which have wavelength sensitivities ranging from 1100 to 2200 nanometer, are mounted onto a spectrograph. While monitoring the conveyor belt, the spectrography rapidly identifies the polymer type and triggers the diversion of the waste, usually by hair pulses, into its proper bin. Simulating very accurately the light propagation and associating this with material property and electromagnetic analysis is a key to the design and tuning of such products. The key metric is a reduction of the rate of false identification of plastic type while maintaining a fast throughput. In that particular case, simulation helps optimize the design of the absorption layer from our efficient process and optimize the head design of the SWIR system for better coupling of the reflected light. Now let's take a look at how simulation can protect biodiversity. And I know it's a stretch, but actually this is a true example. There are more than 60 dams on the Columbia River Basin in the Pacific Northwest region of North America. They created water conditions that are harmful to marine species such as salmon and steelhead trout. The efficacy of any fish passage structure or device or facility or operation or measure is highly dependent on local hydrology, the target species, where they are in the life cycle, the orientation of the dam, the turbine operation, and a myriad of other site-specific considerations. Once again, here we're using computational fluid dynamics to create a model that indicates a strong 3D velocity field in the fishway with eddies, flow separation, vortices, upswelling, and downswelling. We simulate and represent the velocities and the drag forces encountered by the upstream migrating fish and the energy expenditures that they need to consume in ascending the fishway. All of this is based on analyzing the fishway hydrodynamics, and the design can be optimized to improve the passage of the migratory fish. And finally, an example which is still dear to us, face masks. You know that each month, there's about 130 billion face masks that are used and disposed of globally. So if you just take the lightest of these, the surgical mask, it weighs about 3.5 grams. So that's about 450,000 tons of mask a month, 5 million tons of masks to be recycled every year. That's more than 65,000 fully loaded Airbus A320 in weight in comparison. In that particular case, material intelligence is an essential element for design for sustainability. And that applies to all products. In the early phase of designing a new product, the choices of materials rely on accurate material properties, the assessment of the sustainability of the materials in its use, and also when it is discarded, allow you to assign and trace material information throughout the product development and life cycle. Material intelligence is a process by which we combine all material information in one place to facilitate the management of supplier declaration and workflows, and the comparison of multiple materials in order to visualize trade-offs, as you can see on this picture. Trade-offs between different material properties, whether they're engineering properties, economical, or sustainability properties. But the material intelligence also includes manufacturing and processing database to determine the compatibility with a material processing condition. And industry standard properties, ISO properties, make audits more reliable and easier to conduct. The benefit of simulation material properties and manufacturing processes allow to rule out materials that are not compatible with melt and mold recycling process, and filter materials with medical grade availability. In the case of face mask, we demonstrate that it can increase recyclability of products by decreasing the carbon footprint of the product by 2 to 3x over its entire life cycle. And these were just 5 examples. If you're interested, we have 45,000 customers worldwide, so we have thousands of additional examples. But as a conclusion, what I'd like you to leave the meeting with is the fact that engineering simulation is not only a design tool that helps reduce time to market, improves quality and cost, but it's also an essential tool that will help us address environmental challenges and design more frugal, recyclable, and sustainable products. And maybe a quick call to action to all the engineers on the call. Use simulation to invent more. Simulation coupled with machine learning is a tool that allows you to explore more space and innovate for resilience. Do less prototyping for less waste. And train both today's engineers and tomorrow's engineers, not only on improving product, cost, performance, and quality, but also target sustainability and the protection of Earth as one of the key guiding principles of our engineering practice. And now, if you like, I'd like you to challenge me with your comments and questions in this interactive session. Christian?
Yeah, Christoph, thanks a lot for your interesting insights and for your presentation. And Christoph, what impressed me was the cases you had. It's a really big variety, and I think it impressed our viewers too, because I have the question: are these all real use cases? Or to be honest, I changed this question a little. It was about the plastic sorting sorting plant, the sorting system.
Yeah. So these are actually all documented and true examples, Christian. Some of which are done directly by our end users. Some, like the protection of marine species in dams, is done by universities, helping construction and planning. But these are all real examples. We have so many examples of the use of simulation for sustainability that I didn't even have to invent one myself.
Mm-hmm. If you have cases in this broad variety, you should have some experiences. For another question, which industries, in your experience, can benefit most from simulation in regards to sustainability, of course?
Yes. So in general, all industries are moving at different paces towards simulation. Some industries have been using simulation for ages simply because prototyping is not an option. It's too complex. But where the most impact are typically in the automotive and aerospace, oil and gas, wherever material is important. But we see a lot of use of simulation now in agriculture, food processing, construction, and we start to see at a rapid pace adoption of simulation in healthcare. That's a very different way of sustainability. But when we come to customized medicine, we create a lot of one-off products reducing the amount of inventory, so reducing the amount of produced materials that, because of the short lifetime of both drugs and implants in a particular case, get discarded after a very short period of time. So having less inventory is also a way to improve sustainability of a given industry.
I think it was your last slide, or one of your last slides at the end of the presentation. You also talked about less prototyping will lead to less waste. How big of a lever is this in your experience?
Well, it's interesting. We initially thought that less prototyping means that we could bring product faster to market, and that's the historical reason to do less prototyping, because of the complexity of modeling and simulating everything. Take one example: if you want in the automotive industry, if you're developing a autonomous vehicle system, then you would have to run that for millions of miles to test all the conditions. Even if it's an electric car, that's a lot of tires that you're going to use, and from a time standpoint, it doesn't make sense. It's ages before you can bring a product to market. So simulation is a way to virtualize the creation of product. But if you think at systems that are more costly to build, like a satellite or like a SpaceX machine, you don't want to build prototypes. They're way too costly, both in materials and of course their sustainability impact of the prototypes is huge. So yes, less prototype is good for the planet, I truly think.
Sustainability is like a top concern also in product development, of course, or has been a top concern for quite a few years now. Do you think simulation is already a go-to technology?
So simulation is part of the DNA of a lot of design engineers today in a lot of industries. So we've been in business for 50 years now, modeling the laws of physics into computer programs, and it's widely acknowledged and used. What is new and what is a new angle are two main threads. One is what we call material intelligence. The use of very accurate material data throughout the process of prototyping and design, because that has the biggest impact on product recyclability and product impact on planet. And it's also becoming a not just a concern, but a requirement from buyers. People buying your product will ask you for traceability of all the materials in your products. The second angle is the advent of machine learning and artificial intelligence in the simulation and design process. Because taking into account sustainability makes the problem more complex to solve. There are more variables. Machine learning and AI allow you to explore a much wider design space and finding solutions that the human brain, even the most talented engineers, could have come to on his own. And these are the two innovations that are really fueling the deployment of simulation across even more sustainable applications.
If we try from the present to go to the future in sustainable production, what if you could give us an outlook in product design in the future? What will be different in 5, 10, or let's have a bold prediction in 20 years?
Well, 20 years, I wish I still have hairs on my head, but that's another story. So it's what's interesting is what we see as a big change in consumer, but also industrial markets is the era of bespoke products, custom products. Every product, for performance, quality reason, or customer demand, becomes customized to the single user. And every user will have a slightly different, unique product. We saw that recently in automotive industry. There are brands who will make sure that your car doesn't look the same as the next car. But it's true in every product. It's even true in healthcare. Of course, if every product is different, you cannot build a prototype for every product. And therefore, simulation becomes a pervasive tool that will allow you to create a virtual prototype before manufacturing by taking into consideration the parameters given by your market or your customer, and have the tool with more and more automation and artificial intelligence build a perfect product for a particular user. So what I see the industry going toward is leveraging 3D printing, leveraging customization, and very, very fast modeling of the customer environment and the consumer demand into virtual products that are tested, validated very, very quickly, and then manufactured custom for every user.
On our way to this future, to the sustainable product design, what do you think are the biggest challenges for companies, and what qualifications do engineers need that they perhaps at the moment lack?
Yeah, so one of the biggest challenge of designing sustainable product is that, as we said, the decisions are made very early in the design phase, where you don't have all the parameters. So there's a sort of smart guessing that need to take place, or at least give enough variability into your product and refine it along the way. But also, one additional element to the complexity, it's a complete supply chain problem. And the designer doesn't control the full supply chain. So we will need more standards. We will need more methods across the industry to share the sustainability objective and the sustainability metrics in a coherent way. From an engineering readiness standpoint, I think the two innovation, material intelligence and AI ML, are the things I would like my engineering children, if I had, unfortunately they decide to do something else, but to learn, because that will really become one of standard tools in their toolbox, and where we have still a gap between technology availability and the education of our users.
Yeah, thanks. But I've got the big question for the end of our Q&A. And talking about climate change, we are at the moment not looking at an all too bright future, to be honest. What does the world need to stop or better reverse these negative impacts we have?
Yeah, this is a very difficult question, Christian. But what I would say is I'm very pragmatic and Cartesian. I'm an engineer after all, so I trust what I see. But I'm optimistic. I have a strong belief that science, if used the right way by smart people, can help find solutions. It's a collective effort, and opportunities like the one you've given us to talk about sustainability in front of engineering crowd is one of the little elements, the colibri effect, that will make the change happen, because we need to educate more and more and be all conscious that what we do in our daily life, in our engineering life, has an impact on the planet, and it's our responsibility.
Okay, so we hope on science and on smart people.
Yes, always.
Yeah. Thank you very much, Christoph.
No, thank you, Christian. Thank you.
It was a pleasure having you here, and it was really, really interesting insights, I think, with a great impact, I hope, on a better future. Thank you very much, oder vielen Dank, liebe Zuschauer, auch euch, dass ihr dabei wart und uns eure Zeit geschenkt habt. Ich wünsche allen noch einen schönen Tag. Dankeschön.
Vielen Dank.